Hello everyone, I am Sunanta from SNS College of Technology, Department of Mathematics. As the continuation of the lecture series in the Eigenvalue Problems, here we are going to see Eigenvalue, Eigenvector problem solving. So here in this PPT, we are going to see Introduction to Eigenvalues and Eigenvectors, definitions of both. Next is characteristic equation. Next, finding eigenvalues, finding eigenvectors. Next is an example problem. Next is example eigenvalue finding and example eigenvalue eigenvector finding. Next is the applications of eigenvalue and eigenvectors. Let us dive into the PPTs. So first is introduction to eigenvalue and an eigenvector. Here the core tools are serve as fundamental tools for understanding linear transformation and matrix behavior. So in data science, crucial in dimensionality reduction techniques, extracting key data features. Next, in engineering analysis, modeling and analyzing structural stability, resonance and natural frequencies. Next is definitions of eigenvalue and eigenvector. So eigenvalue, here we are going to denote it by lambda. So lambda denotes the eigenvalue, a scalar representing how much the eigenvector is scaled by the transformation. Next is eigenvector, it is denoted by V. So V represents the eigenvector and a non-zero vector that maintains its direction after the linear transformation. And here we are going to take the equation as AV equal to lambda V. So A is a matrix, B is an eigenvector and lambda is an eigenvalue. So next is in characteristic equation. So the characteristic equation is given by the determinant of A minus lambda I equal to 0, which arises from seeking a non-trivial solution to AV equal to lambda V. So on rewriting this equation, which can be as A minus lambda I into V equal to 0, which will fetch the eigenvector. Next is finding eigenvalue. So it will be found by A minus lambda I. This is an invertible, non-invertible. So determinant of A minus lambda I will be equal to 0. Next is finding eigenvalue. So first we are going to construct A minus lambda I. So form a matrix A minus lambda I by subtracting eigenvalue from the diagonal elements of the matrix A. For example, if we are having a 2 by 2 matrix or 3 by 3 matrix, if we take lambda as the eigenvalue, then in the diagonal elements we are going to subtract that A lambda from the main diagonal elements. So next is finding the determinant. So after writing A minus lambda I, we are going to find the determinant of that matrix. So A minus lambda I. So on calculating that, we will get an equation. So next is solving determinant of A minus lambda I. So on finding the determinant of A minus lambda I, which will give a polynomial. So on solving that polynomial, we will get the values of lambda. So if we are having 2 by 2 matrix, we will get 2 lambda values. If we are having 3 by 3 matrix, then we will get 3 lambda values. If we have 4 by 4 matrix, we will have 4 lambda values, so on. Next is finding eigenvectors. So after finding the eigenvalue, we are going to apply A minus lambda I into V equal to 0. That is 1 by 1. We are going to apply the lambda value, and using Gauss elimination method or some other equation solving methods, we will find a matrix which will be a column matrix, which is called a eigenvector. Next is example problem solving setup. So first one is problem objective. So we aim to determine the eigenvalue and eigenvector V associated with matrix A. Next is defining the matrix A. So the matrix A is defined as 2 by 2 matrix. So in the first row we are having 2, 1, and in the second row we have 1 and 2. This will be the matrix we are going to use. So next is solving eigenvalue. So we are applying the same concept. So we on finding computing determinant of A minus lambda I, we have 2 minus lambda comma 1 and 1 comma 2 minus lambda in the second row. So we get the characteristic equation as lambda square minus 4 lambda plus 3 as 0. So on solving the given polynomial, second degree polynomial, we will have lambda equal to 1 and 3. Next is solving for eigenvector. So first we are applying lambda equal to 3. So we get minus 1, 1, 1, minus 1 in the values. So on solving that, we will get the eigenvalue to be equal to 1, 1. Next, on applying lambda equal to 1, we will get 1, 1, 1, 1, which is equal to null space. When we get 2 rows or 2 columns identical, then that matrix will be equal to 0. So it is 0. Next is applications of eigenvalue and eigenvectors. So first one is principal component analysis, so which reduces data dimensionality while retaining essential features, simplifying complex data set and enhancing analysis. Next is vibrational mode analysis. So in that, analyzing vibrational behavior in structures like bridges, buildings, ensuring stability and preventing resonance induced failures. Next is solving differential equations. So for solving differential equations, we can use this concept. Next is, these are the references. Thank you.